Cześć wszystkim, nazywam się Bartosz Pampuch. Mam pytanie, czy mamy na sali osoby niepolskojęzyczne? Okej. Super, super, bo bałem się, że będę trochę z siebie błazna robił, mówiąc po angielsku. Zostałem poproszony, żeby sesja była prowadzona po angielsku i tak sobie myślę, no nie chcę tutaj wyjść na takiego człowieka, który się wydurnia, więc, ale skoro mamy, to bardzo się cieszę. Dzięki, że przyszliście. Thanks for coming. So yeah, I'm going to talk about Stable Diffusion today. I have over 90 slides and I guess 35 minutes, so we better start. So I'm going to start with the user's perspective, because how many of you have ever used Stable Diffusion? Quite a lot. How many of you have ever used ControlNet? Not that much. Okay, so the user's perspective might be actually quite important. So as you know, Stable Diffusion is a generative model or a set of models actually, and it is mostly known and famous because of this text-to-image capability, which allows us to generate an image from a prompt, from the text. So the thing that you see here is called Web UI. It is something that you can install on your computer, and it allows you, it's not very intuitive in terms of the user interface, but it is something that allows you to touch every single point of Stable Diffusion. So I highly recommend playing around with this thing, because it allows to learn a lot what's possible or not. So basically, the very first thing you do is you type a text, like a text prompt, like a portrait photo of a black girl smiling, etc., etc. So the more you write, the more precisely you describe the prompt and the thing that you want to be generated, the better result is. So yeah, I got this image, but this kind of stuff looks more like a stock, right? Instead of searching for images and getting the picture, you just type the prompt, which is kind of search engine, let's say. I mean, there's this analogy, and you get the picture, right? But the thing is that it's generated. Luckily, Stable Diffusion doesn't finish here, so we have other features that we can leverage, such as image-to-image. So image-to-image allows us to upload a picture and use it. So let's say that we have this picture, and we can describe it like a movie poster, young blonde woman, ocean, earth in the sky. And I can regenerate this image and get something very similar. It looks much similar. It's quite yeah. The resemblance is very well pronounced, but clearly this is not the same girl anymore. So we have like another picture right here. We can of course generate more such images, because the entire process is stochastic. So we can generate as many pictures as we wish, and they will all differ. So we can keep doing this until we find something that we really like. Now, this image-to-image functionality allows us to select the denoise level. So it's kind of how much we allow Stable Diffusion to change the original image. So I can put it all the way up, maybe not all the way up, but slightly higher, and change, for instance, part of the prompt. Instead of Earth in the sky, let's try sharks in the sky. And if I do it and click Regenerate, I got quite interesting results, because the girl has changed a little more, and instead of the earth in the sky, I got sharks in the sky. Of course, the text is corrupted, but that's obvious. We allowed Stable Diffusion to make further changes, so this is the side effect. But still, it is quite cool. I can also do something that is called in-painting. This is part of the workflow that we usually do when we use Stable Diffusion. It differs from Midjourney, for instance. So let's assume that I want to give or add a scarf onto that picture. So what I can do is I can put this image into in-painting, draw a mask over the neck, and change the prompt to scarf. And if I type generate, I get a scarf which is perfectly placed on this image. So and this is the way we usually work with Stable Diffusion, by gradually adding parts of the image or modifying parts of the image and reshaping it in the direction that we want to. So yeah, and we can do it many times as long as we don't like the results, to get something that we'll be happy with. The next great feature of Stable Diffusion is outpainting. So we have already seen in-painting, but there's also outpainting. So imagine that we have the original picture. It doesn't have to be a generated picture. You can get like your photo from holidays or whatever. And let's assume that we want to get the other parts of the pictures that are not available here, like to the right and to the left, right? So what I have to do is I have to change the prompt because I don't want to have another girl in that part of the image. So I can select the part of the prompt that describes the girl and simply remove it. Just leave the tavern description over there and click here where I need something new. And after a few seconds, I get a set of pictures that I can choose from that are like the extension of this image. And I can do the very same thing on the other side, like this. And as you can see, this is fabulous. I mean, this is something that allows you to get something that you need. So by default, we get 4 pictures that we can choose from. But if we don't like it, we can just click Enter, and we get another 4, and so on. But something that is totally mind-blowing and much better than what we've already seen here is the ControlNet. And I'm happy that not many of you have already seen this because, yeah, it is absolutely insane. So Stable Diffusion allows us to use additional models. I'm going to talk about what it works like and what's behind this. But basically, from the user's perspective, the idea is that you can upload a picture like this one here and say, I would like to have the pose of the generated image to resemble this one. So ControlNet gives us this possibility to use, it provides preprocessors like, for instance, this canny edge preprocessor, which detects edges in the image, and then a set of models that are kind of additional conditioning on top of Stable Diffusion. And if we generate our image now, just take a look at this. We get an image of the same girl, but with this particular pose. This is insane. And there are several models that ControlNet provides, like models that allow you to, rearrange your house. You take a picture at your home and say, describe what you want to get there, and you get a new picture with a new rearrangement and things like that. So it is really cool. And if you want to play with these things, these are the links. The presentation will be available, of course. So you can download Automatic 1111 is a kind of single-click installer for the entire environment. You can get a lot of models on civitai.com. So this is a website with over 1,000 models that are available for Stable Diffusion that were trained on different sets of images. So they can give you different style, but also some were trained on human images. So you get better anatomy and things like that. And ControlNet is available on Hugging Face. Now, how does it work underneath? How is that thing even possible? So Stable Diffusion is not a single mechanism. It's actually a set of different networks and components that come together. So we first have variational autoencoder, which is the point, is the component that lets this mechanism work efficiently. I'm going to talk about it later. But the general idea is to let the Stable Diffusion work with low-resolution images instead of high-resolution images. And it's really very performance-wise. There's the denoiser, which is like the heart of the entire Stable Diffusion. And there's the conditioning part, which allows us to not only generate the images, whatever images Stable Diffusion can come up with, but rather force the Stable Diffusion to generate what we are actually looking for, what we need. Now, if you read the original papers or blogs or whatever, they usually start talking about or describing Stable Diffusion with this kind of information. So they say, okay, we get an image, and then we gradually corrupt this image by adding Gaussian noise to finally get the pure Gaussian noise at the end. And then we somehow reverse the process to get back to the image. And, you can read this and you're like, what? What's going on here? Why is this even crazy idea gonna work, right? We have no idea. So I don't like this approach to define say how how Stable Diffusion works, because it's hard to get it. So what I like instead is to try to go through the generation process first, not the entire training and things like that, but rather the generation process to understand what happens when we try to generate the image. So everything starts with a prompt, right? Assuming that we are in the text-to-image mode. So we can write something like cute and adorable bunny, blah, blah, blah. And then this text is tokenized, so each word is tokenized, and we get 77 tokens that are passed through text encoder. So eventually we get the embeddings that represent this text that we have written in a semantic way. Basically, this text encoder is a transformer that was trained on pairs of images and their descriptions. So there were actually two encoders, a text encoder and an image encoder, that were trained together, and they share the same embedding space, which we can treat as like putting images in this multidimensional space and training both encoders so that they produce the same or very similar embeddings for similar pairs of images and descriptions. And those that do not match, the descriptions that do not match text, are actually in that space far away. So this is how they train this thing. Stable Diffusion uses CLIP, which stands for Contrastive Language Image Pre-training, and it is developed by OpenAI. But they actually updated in the Stable Diffusion to use OpenClip, but the initial Stable Diffusion used Clip by OpenAI. Yeah, Clip is also a good image classifier, a zero-shot image classifier that you can also use as a standalone mechanism. But it's actually a crucial part in Stable Diffusion as well. So when we have this prompt, when we have these embeddings, they go to this denoising part through the cross-attention mechanisms. So it's kind of similar to what we have in transformers architecture when we combine encoder with decoder, right? So if we do machine translation, for instance, so we have the encoder and there's the cross-attention module in the decoder that can join these things together. And this is actually quite similar here when we kind of join the images that are being generated with the embeddings, with the conditioning part, to somehow guide the process towards the right thing that we are looking for, and to actually learn through the attention mechanisms, learn the relations between these things. But this is not that important right now. Let's focus on the denoiser as a general idea. So to understand how denoising processes work, let's take a look at this image. So we know what it is. It's a dog, right? And I'm going to corrupt this image a little bit by adding these red dots, rectangles, squares, whatever. And if I asked you what is the noise on this image, you'd probably have no problems to say that this is the noise, right? These dots, red dots or red squares, are the noise. And this is because we have seen so many pictures of dogs that it's obvious for us, right? If I showed you this picture, this one, you would also probably have no problems to say what it is, right? Maybe it would be quite difficult to draw the noise out of this image manually by going pixel after pixel. We would do it probably, but it would take time. But still, it's still doable for us. It is still feasible. Now, take a look at this. What is on this in this picture? You have no idea, right? I don't either, because we haven't been trained on such images. We don't see them too frequently in our life, right? So this is too difficult for us to decide what is here. Now, this is the advantage of the denoiser, because it's kind of better than human beings in finding this noise, because it's been trained on noised images. So it's like you know, it's been given that we had this image, this dog. We gradually corrupted this image and had a lot of steps. So we know that in the first step, this can look like this, in the second like this, and so on and so on and so on. So for the denoiser, this image is actually something that it has this you know, it can learn on. So we can teach the denoiser and tell, this is the image. We know what the noise is here because we have generated it. So just learn how to detect this noise. The smart people also figured out that using the linear schedule to add the noise corrupts the image too early in this process. So they changed the scheduling mechanism to cosine to have like more features along the way and get the corrupted image just at the end of the process. So this is how the denoiser is being trained, and thanks to this, what we can do is to give a pure noise to the denoiser and say, okay, there's a dog on this image, or at least we want there to be a dog. And denoiser, tell me what is the noise of this image if what I expect is the dog. So the denoiser does its job and says, okay, this is the noise of this image. So what do? We subtract the predicted noise from the image. What do we get? No, this doesn't look good, right? So the denoiser is not that smart to be able to predict the noise out of this pure Gaussian noise. But we somehow believe that at least it leads us in the right direction. So we believe that maybe it's not very accurate at the beginning, but it knows somehow that we should go in that way. So what we do instead is we add another component called sampler. And the sampler takes this noise predicted by the denoiser, but just a little bit of it. Not the entire noise, but just part of it. And subtracts it from the image and gets a new picture that is slightly less noised as compared to the original one, and the process is repeated. So after several steps, we get a situation where this denoiser guides the sampler where it should go, and the sampler somehow believes at the beginning less and at the end of the process more to the denoiser and heads in that direction, and also adds a little bit of noise to get better results, but it's not that important for now. So as you can see, after several steps, or many steps in this case, 50 steps, we get a bunny. If you want to take a look at the thing that I have just presented, these slides, not slides, but the things that I had on these slides were taken from Diffusion Explainer. It's available on PoloClab, GitHub.io. So it's a website that allows you to see what it looks like. It's not exactly the entire process that is described there, but more or less it's a good explainer. So yeah, we have this denoising part, the sampler, that allow us to get to an interesting image out of pure noise. This is actually quite interesting, but the problem is that this image is 64 by 64 pixels. So definitely not something that we want to see as the final result. It has 4 channels, to be honest. It's not RGB 64 by 64. It has 4 channels, but still, its dimensionality is pretty small. And this is where variational autoencoders comes handy, or even crucial, I would say, because it allows us to get that 64 by 64 image and turn it into 512 by 512. Ridiculous, right? How is that even possible? Well, let's see. So to understand this, we got to talk about autoencoders. I'm pretty sure that a lot of people here, or most people, know what autoencoders are, but for those who don't, so the autoencoders architecture is like, it consists of 2 parts, an encoder and a decoder. So the encoder takes an input and transforms it maps it into the latent vector and reduces its dimensionality, while the decoder takes this latent vector and tries to recreate the original image. So the idea behind autoencoders is to get at the output something that is as close to the input as possible. Now you may wonder, what's the big? I mean, maybe not what's the big deal, but what's the idea behind this? Why do we make a network that recreates the same thing that it has on the input, right? It doesn't make sense, of course, but the sense lies in this latent vector in the middle that is also called the bottleneck, because it allows us to reduce the dimensionality of the original input. So imagine that I have like a couple of pictures of dogs, and I put them to the autoencoder. It has to reduce the dimensionality, which means that it has to detect the features that are relevant and that will allow the decoder to recreate the original image. So let's assume that this three-dimensional space that we have here in this room is this multi-dimensional space, and the encoder goes with the images of dogs and puts them in that corner. Now it gets the images of cats and puts this into another corner. So essentially, at the end, we get the latent vector that has just 3 dimensions in this room, right? X, Y, and Z. And they describe the exact position where this picture is. So the decoder somehow knows how to reverse this, recreate this process, by getting just these 3 coordinates, right? Just these 3 numbers. So if I put this, the coordinates of this corner to the decoder, it will recreate the image. So it is cool, but unfortunately, the space is very sparse. So there are some pictures in that corner, there are some other pictures in that corner, but most of the space is empty. And if we add like a random vector to the decoder, what we will get will be just noise, nothing more. And this is the reason why autoencoders are not the best generators in case of imaging or whatever. They are just good compressors. And so what we would like to have instead is to limit the entire space to something smaller, like this circle, and ask autoencoder to put all the images, to shape this space in such a way that, first of all the images are within the circle, because then we'll be able to sample this space to get something that looks good for the decoder. So this is the first thing, to limit the space. And the second thing is to shape this space in such a way that similar items are located close to each other and that the space is continuous, meaning that every single point in that space gives us a relevant result, an image that looks good. We don't want to have data points over there, vectors, that would lead to noise after the decoder's work. So this is exactly what variational autoencoders do. So variational autoencoders, they don't they don't map the input to the latent vector, but rather to the probability distribution parameters. Like we can say, okay, we want to use Gaussian distribution, so we are going to have mean and the variance, or right in this or standard deviation in this case. So there's like pairs of parameters that describe the image, not just its position, but actually the distribution. And we sample from that distribution to get the vector that we put then to the decoder. And the funny thing is that it actually works and does exactly what I've said. So we get a continuous space with elements close to each other. How do we do this? How do we build those variational autoencoders? Well, variational autoencoders leverage bias theorem, which describes the relation between various probabilities. So we can get from the bias theorem that the probability of conditional probability of A given B equals this, right? So these things are called posterior, likelihood, prior, and normalizing constant, also known as evidence. And if we switch those A and B's into Z and X, where Z is the latent variable and X is the actual data, we see that P probability of Z given X is actually our encoder, because it means we will give an image, we will provide the image, and calculate, get the Z, get the latent vector, right? Sorry, in this case, not the latent vector, but the distribution that describes, so the parameters of the distribution that describe this in the latent space. And also the likelihood is the decoder, because it reverses the process. Given the Z, I want to get X. I want to get my image. So we could think that, okay, so all we have to do is somehow calculate this. The problem is that in order to calculate probability of Z given X, we have to know what the evidence is. And to calculate the evidence, we have to calculate the integral over Z, over the entire latent space. And usually, it is intractable. We cannot do it easily in an analytical way. So what do we do instead? We approximate this P of Z given X by another, simpler probability distribution that is actually a neural network. And we do this. We want them to be as close to each other as possible. And to do this, we want to minimize the Kullback-Leibler divergence, right? So I'm not going to, we don't have time to go through this entire thing. I know what it looks like, don't worry. It sounds like, what is this guy even talking about for people who don't do it on a daily basis, of course. And yeah, it quite much, I would say it differs from let's say, this picture. Yeah, this is the same session. But still, this isn't that complex, to be honest. I mean, it's just a set of simple transformations regarding logarithms and things like that, things that we have learned in high school. But if you take a look at this later, it's quite simple actually. But the thing is not the math behind this. The thing is that at the end of these transformation, we see that there are actually two terms in this entire thing. And it turns out that all we need to do to let the variational autoencoder do what we need is we need to calculate the reconstruction error between the generated image and the one that was given at as an input, and Kullback-Leibler's divergence between the approximate posterior and prior, where prior is usually Gaussian, because we want to put all these images into this circle, right? Multidimensional circle to get all things out there. There's also one trick that needs to be done to let variational autoencoder work, or actually to be able to train them, because as you have seen in the original variational autoencoder, we get the probability distribution, and we have to sample from that probability distribution to get the latent vector that goes to the decoder. And this is a stochastic element because, you know, sampling is stochastic. So the backpropagation will not go through these elements. I'm using my cursor, but somehow it's not visible. Anyway, so you have to use your imagination and see what I'm talking about. Yeah, there's a little trick that is done here, that is being made here. So they put this stochastic element out of this backpropagation route, so it's possible to teach this network. But anyway, so we have this variational autoencoder that works and is trained in such a way that I have presented, and this is the left part. The left part that allows us to get from such an image, when it's being trained, you see this is a parrot, and turn it into this set of pictures. So as I said, no RGB, just 4 channels, but much smaller, 64 by 64. So this is what the encoder produces. Now the decoder can take this and recreate this parrot just like this. You see, the parrot to the right is recreated from the 64 by 64 images. It is absolutely brilliant. Of course, it has troubles with some images, especially eyes, right? When you generate human faces, sometimes those tiny things do not work as expected. So we have to use other networks that are also available in the web UI software that I've presented. So you just have to check to fix the faces, and it actually runs the output through another network that fixes those parts. But still, this is brilliant because it allows us to use Stable Diffusion on our PCs at home. So the math behind denoising process is slightly more complex. And just to give you a little glimpse overview, there's a very cool 30-minute long video on YouTube that describes how the math behind it. And this is the speed. This is not like twice the speed. It is the original speed of the other that for 30 minutes talks about this thing and talks, this goes here and that and there and there. So if someone is interested, just watch it. But to be honest, it's not the math that is important for us to understand now, but rather surprising conclusions that come out of this math, and they are actually quite simple. All we need to make this work is we need a network that will be trained on a diffused picture, given the time step, and will be supposed to detect the noise. And the loss function in this case is just a mean square error between the predicted noise and the original generated noise. So what I presented a few minutes ago. So actually, we don't need the entire math. Of course, it was required to get to these conclusions. But after all we need is a simple network that will be able to do this. And the network that does this is called UNet. UNet is a network that was primarily used in medical imaging segmentation to segment those images. But it's actually quite similar to encoder-decoder philosophy. It has a set of convolutional blocks, also max pools. So basically, it works like there's this contracting path and the expanding path. So in the contracting path, it works like a normal convolution network, I would say, that detects the images, the features out of those images. Then we have max pooling, so we decrease the spatial dimensionality, but increase the set of features, the set of channels, double the set of channels. And it goes like this until this bottleneck over here. And then this goes through the expanding path with transposed convolutions, and so it upscales the image back to the original size. We also have something, skip connections between the blocks that have the same resolution, and it allows the network during the reconstruction phase, the upscaling phase, to also leverage the local features that were detected here but then got lost over here. So it's actually quite good at segmentation, but it turns out that it's also good at detecting the noise. It can be trained because it has the same size of the input image and the output image. We get like the same dimensionality on both sides, so it can do a lot of fancy stuff. And it is also extended a little bit, so the original UNet was slightly modified. So instead of convolutions, we have ResNet blocks, we have attention blocks, we have time steps embeddings to let the UNet know which time step of this entire diffusion process it is working on. So basically, that's it. And the last thing, and this is how it works. So it's able to detect the noise and be part of this puzzle. And the last thing I wanted to talk about is ControlNet. How does this thing work? So it's actually very brilliant mechanism because it extends Stable Diffusion without changing it. So, we have Stable Diffusion, a huge model with millions of parameters that, people don't want to retrain the entire thing because it would take time. We could also make the network less performant. So what they do instead is they kind of freeze the original network, Stable Diffusion model, and they teach another network that actually just learns how to modify parts of the Stable Diffusion. It's like a hyper network, right? It kind of modifies this Stable Diffusion by learning how to change UNet. So this is exactly as you see. This is UNet. This thing to the left. It's just not. It doesn't have this U shape because it's drawn here from top to bottom. But actually, this ControlNet just has a very similar UNet and adds the results over here. It's just simple adding. It's summing its results to the results that the original UNet does. And they train it on several data sets. So for instance, Canny Edge, the one that I've already told you and presented, told you about and presented at the beginning. So just take a look. These are the edges, the Canny edges to the left, and these are the images that were generated by Stable Diffusion using the Canny Edge model. They also had hue line that is perfect for regular shapes, such as straight lines, as I said, for architecture or your homes. There's this scribble network that allows you to draw something like this. This is fabulous. Just think about your kid that can draw something like this to the left, and what you get are the results to the right. There's also open pose, where you can use, draw a pose and generate a person that has exactly the same pose. There are segmentation maps, so you can say, I want to have sky over here and grass over here or whatever, and generate such images. There are normal maps. There are, a lot of things. And people are really crazy. Just take a look what they do with ControlNet. This is insane. This is the creativity that people have and know how to use these things. Okay, so that's it. Thank you so much for your attention.